So today we will expand our discussion on the structure of electromagnetic theory, and we will try to see how do we gradually move toward the usual quantization which we have learned for other two fields, namely the scalar field as well as the Dirac field. So as you recall from our previous day discussion, what we have at our hand is in terms of description of electromagnetic theory is a vector potential AMU which has four components. Now we know that these four components do transform as Lorentz vectors, so therefore this is a theory of vector degrees of freedom. So AMUs constitute that, and we saw that in a particular gauge, which is the Lorentz gauge over here, which is named as the Lorentz gauge over here, they satisfy the wave equation, the usual Klein-Gordon equation which we have learned for scalar field as well as for Dirac field. The vector fields also seem to satisfy the same kind of Klein-Gordon equation structure, subject to a condition which is the gauge condition which we are talking about is the Lorentz gauge. Okay, Lorentz gauge previously we had written in terms of a divergence of the 3 vector A and 1 over c square times the divergence of the time derivative of the scalar potential phi, they should add up to 0. That was the condition we obtained in order to get the wave equation for all of the AMU's component. Now we can, if you pay attention to the fact that this equation, which is the gauge equation, can nicely be written in a form which is del mu a mu. If you open it up, you will get this equation back. What is the benefit of writing it in this way? One thing, it is compact, but more than that, you can see that this is a scalar equation. There is a covector and vector summed over. So ultimately it transforms like a scalar. That means it doesn't transform at all. So if you satisfy this condition in one frame, one inertial frame, this condition will remain true under all inertial transformation generated via Lorentz transformations. So therefore, if we have a wave equation for the degrees of freedom a mu, then subject to one gauge condition, this condition is realized in a particular gauge, then the statement remains true in all inertial frame which are connected from the your initial inertial frame via Lorentz transformation. Okay, so far so good. We have an equation which can be trusted, which is transforming like a vector, and the wave equation remains the wave equation because the gauge condition under which it has been obtained remains the true gauge condition even if I go to another inertial frame. Now the idea is, should we go ahead and quantize a mu just like we had done before? We need to see whether if we quantize a mu, do I get something which is problematic at hand? For example, for Klein-Gordon case, the scalar field which was satisfying this equation got quantized very effortlessly and there was nothing serious about it. But when we try to do the same thing for the Dirac or Spinor field, there we realize that we do not have to rely on the classical structure. We actually have to give it up and envisage some new kind of relations between the phase space variable, which is unseen for a classical system. So that came about as the anti-commutator. So let us try to see whether if I go ahead and quantize this 4 degrees of freedom, do I get a meaningful, consistent Lorentz invariant description without any problem? That means it's Hamiltonian and other aspects are under control or not. Okay, so we will go towards the quantization of this, but let us spend some time in understanding this structure of the AMU with slightly more rigor. Now, we believe this wave equation is the story of electromagnetism. So somehow the whole of electromagnetism should be contained within this. It is not that such that I'm just quantizing some effective equation which I have landed upon accidentally. Because in deriving this equation, remember, we use Maxwell's equations one after another. So idea is whatever I'm going to quantize, whatever I'm going to do should be describing not just one equation of coming from the Maxwell's equations, but the whole of Maxwell's equations set should be contained by AMU. So if I can quantize AMU, I should be getting a result that ultimately all electromagnetic field component get quantized as well. So therefore, we should be aware that how to write things which appears in electrodynamics in terms of AMU, and what does it mean to quantize AMU, whether the full action which gives rise to the equations of motion, which is consistent with Maxwell's equation, is getting quantized or some other Lagrangian is there. So we would hope that we get some Lagrangian whose variational approach gives me equations of motion which are just the Maxwell's equations. Okay, all right. Now there is, if I pay attention towards the structure of equations of motion of this A mu, that means the physical quantity is made up out of it, electric field and magnetic field, they nicely separate into two sets of Maxwell's equation each. So first, the usual way of looking at Maxwell's equation is look first for the equations of motion for electric field and then write down the same thing for magnetic field. However, if I just look on this particular structure, divergence of E and curl of B, this set of equation, this is a scalar equation, this is equal to 0, and while this is a vector equation, which is three component of it. Now look at these equation individually. If I just open it up, the divergence of electric field is equivalent to divergence of negative of a particular quantity, which was gradient of phi and time derivative of A. So this was the definition of electric field in electrodynamics. Remember, if electrodynamics is electrostatics, meaning there is no dynamics, then the time derivative part goes away, and I get the case of electrostatics where electric field is just minus of the gradient of some scalar potential. But if electric field is dynamically changing, then this equation is true, that electric field is gradient of phi plus some temporal derivative of a vector potential. That should be 0. Okay, this is good. Now take this divergence inside. Divergence will go inside and hit this gradient term and convert into Laplacian of phi. I will get a Laplacian of phi from the first term. The second term goes and hits the A. So I will have a time derivative of divergence of A. Again, I have taken the divergence inside because partial derivatives commute. Order doesn't match. Which order I do? Order doesn't create a matter. It does not matter and does not create any problem for you. That first you do temporal derivative, then you do partial derivative with respect to space, or vice versa, you get the same result. So that's why I have taken the divergence inside the A, and then I have used the gauge condition. The gauge condition is the divergence of A is 1 by c minus of 1 by c square and temporal derivative. That makes this temporal derivative of a divergence of A is equal to minus of 1 over c square double derivative of a scalar field with respect to time. So ultimately, there was a Laplacian in space and then a temporal derivative with respect to time came about, and there was a minus sign already outside. So ultimately you will get a structure that 1 over c square del t square with a positive sign and then a minus of a Laplacian, everything hitting the phi. Okay, it should be 0, which is box of phi is equal to 0. Box of phi, remember, up to a division by c was a naught, a upper index naught, which is 0th component of the vector potential, 4 vector potential. So a mu the 0th component satisfies this equation. And again, the second set of Maxwell's equation which we are considering is the vector class. Curl of B is equal to 0. You can do the algebra again, write down B is equal to curl of minus A, the curl of A, use the curl of A into something and use the gauge condition again. You will be able to show that that equation is also equivalent to writing as that box of A, vector A is also 0. So you see individually all the components of the vector potential A mu, this equation, are coming just from the two sets of Maxwell's equation. But Maxwell's equation is set of four class of equation: scalar equation for E, vector equation for E, scalar equation for B, vector equation of B. So therefore, whether if I quantize this theory up to this much, am I quantizing the full electromagnetic theory? Only half part of it. That is the second two Maxwell's equation as well only. And what do we do with the remaining two? Actually, now if we see the way we have defined electric field and other things, the gauge condition, whatever we have wrote down, this does not require you to do anything. The two remaining sets of Maxwell's equation get satisfied automatically just from their geometric structure. Why is that? First, remember, we have decided to call magnetic field as a curl of A. So therefore, divergence of B is equal to 0 is automatic. Once you write like this, divergence of B cannot be anything else, but it has to be 0. So the third Maxwell's equation, let us say, is just an identity corresponding to this definition of a B. Okay, so you do not have to do anything, you do not have to solve anything. Divergence of B will always be 0 given the structure of B. What about the last remaining Maxwell's equation? Curl of E is equal to minus del B of del T. Again, write down the definitions of E here and definition of B over here, and use for the fact that the gradient of a curl is 0. Sorry, curl of a gradient is 0. That is also geometrically true. Curl of a gradient is always 0. You do not have to do anything or solve anything. Then this both sides become the same thing and they are automatically true. So remaining two set of Maxwell's equations are not governed by any equation of motion like wave equation. They are just geometrical identities. They will be true even if the a mu did not satisfy the wave equation. In deriving this, we never used the wave equation solution or anything. So the two sets of Maxwell's equations are not equations of motion. They are geometrical identities. The remaining two sets of Maxwell's equations here, they are physical conditions. They require certain conditions on a mu. How will it propagate, with what speed and what not. Okay, very well. So now with this information, we try to go forward and try to see the structure of a particular Lagrangian which would be able to give me the first two sets of Maxwell's equation, which are only the equations of motion, or the box of mu, which is made up from these two, is effectively this equation and this equation collectively are this equation and that equation. Vector part is, meaning the zeroth part of the wave equation is the first Maxwell's equation. The remaining three vector part is the third Maxwell's equation, so to say. So therefore, those are only the dynamical equation. Remaining the second Maxwell's equation, divergence of B is equal to 0 and curl of E is equal to minus del B upon del T, which is the fourth Maxwell's equation. They are just geometric identities. So we should look for a Lagrangian which generates for me correct first two equations of Maxwell, not first two, first and third, which is equivalent to finding a Lagrangian which gives me the box of a mu is equal to 0. Okay, I hope this is clear that all the dynamics of electrodynamics is contained in the first and the third Maxwell equation, and this is covered by overall by this wave equation. The remaining two Maxwell's equations are not dynamical equations. They have to be true at all times because of a geometric identity. Okay, so let us try to get a good meaningful Lagrangian in order to write down that, and from varying that, let us hope that we will get the box of mu is equal to 0. All right. Now, in order to do that, it is convenient to write down the variables a mu's and physical quantities, electric field and magnetic field, in a particular appropriate relationships. You might have seen it in the covariant discussion or Lagrangian formulation of electrodynamics already. If not, I will just go through very quickly over it, and you should look at any good book of electrodynamics to just revise or re-look at this idea. So we are going for vector potential a mu, whose components are the scalar potential and the current density. Sorry, the A over here, I have written wrongly. The vector potential A. I should have written as A. Somehow I had written erroneously as J. But anyway, this is fine. I have corrected it. So I have a vector potential whose first component is scalar potential, and the remaining three components are the vector potential generating the magnetic field. Okay, so in terms of electric field, how do I express electric field in terms of these variables? Electric field, remember, is gradient of phi and temporal derivative of this, and with a minus sign. So you do that. Remember, this object up to 1 over c will be that object up to 1 over c would be the first component a0. So ultimately you can see that we are writing things like electric field is like del a0 upon del x minus del ax del x0. This is the temporal derivative, and the component x component will come from x component of this and x component of that, which is equivalent to this. Similarly, if I write down what is the y component of this, I would plug in the y component of the gradient and y component of the temporal derivative, which is over here. And similarly for z component, I will just take the z component from here, the z component from here, and the z component from here, the second the second kind, temporal derivative and the spatial derivative itself. Okay. In this process, I have generated things which are lower index object. You see, in doing so, you will realize that our discussion from special relativity, the lower index objects are to be obtained from a contraction of the upper index quantities through the Minkowskian metric. So if A upper mu was given as phi over C and vector potential A, I should obtain the lower index object as A lower mu as eta mu nu A nu. It should be A nu over here. Nu is being summed over. Okay, so there are a couple of typos in this. You should correct in your notes. Now we see that the electric field is made from the A with their antisymmetric derivatives. That means if 0 appears here, x appears here. In the next term, x appears here and 0 appears here. For Ey, 0 appears here, y appears here. In the next term, y appears up, 0 appears down. And similarly for z. So they are made from the antisymmetric combinations of derivative terms. So electric field is made from the derivative of x and 0, meaning the indices are appearing at x and 0. For y, the indices are appearing y and 0. For z, indices are appearing as z and 0. So overall electric field can be written in terms of A. They are made from AI and A0. I index is the electric field index, and you would have this structure. Okay, so this is how we write down the electric field in terms of the vector potentials. What about magnetic field? Magnetic field, we know they are obtainable from the curl of A directly. So x component of magnetic field will be del y az minus del z ay. So whatever we discuss about the electric field, the same indices were appearing in the A and in the derivative. In the case of magnetic field, you see if x is appearing here, none of the derivatives or the components are x. They are the other two indices. Similarly for y, the z and x will be appearing over here. None of the indices in this derivatives will be y. And similarly for z. So together, due to its curl product kind of structure, you see already they are antisymmetric in y and z exchange. So antisymmetric structure is maintained like electric field, but the indices structure is slightly different. For electric field, the indices appear in the derivatives and the terms. In magnetic field, the indices does not appear in the derivative and the term. So this is compactly written in the equation like this. This is written in with something called the Levi-Civita tensor. Levi-Civita tensor. That tensor is epsilon ijk can take various values. The idea about this that one normal ordering will be 1, 1, 2, 3. Cyclic ordering of that also be 1. For example, 3 goes to 1, 1 goes to 2, and 2 goes to 3, which will be 3, 1, 2. That will be also 1, and so on. That E2, 3, 2, E2, 3, 1, for example, will also be 1. However, if I exchange any of them, E1, 3, 2, which is just 2 and 3 interchanged, that is minus 1. Similarly, E3, 2, 1, that is all equal to minus 1. So this is antisymmetric tensor in all of its indices. If j and k are interchanged, it will pick up a minus sign. If I and j are interchanged, it will pick up a minus sign. If I and k are interchanged, it will pick up minus sign. So using that, you can see that this terms over here can be written in terms of a Levi-Civita symbol or Levi-Civita tensor like this. So collectively, I see both the magnetic field and electric field are coming from antisymmetric derivatives of the vector potential. So I'm going to define set of all antisymmetric derivatives of the vector potential as something that is called the field strength tensor, F mu nu. F mu nu is the collection of all antisymmetric derivatives of A and vice versa, meaning del mu A mu minus del mu A mu. So you see some of the components of this will be electric field because they are some components of the antisymmetric version, and some of the components will be magnetic field because they are also antisymmetric derivative of the same kind. You can quickly identify and realize that F0I, if I put 0 here, I here, there also I would have a 0 here, I here. Then ultimately I will get here I here and 0 here. That is equivalent to my definition of electric field's ith component with a minus sign. So f lower 0 I is minus ei. Fij is epsilon ij k bk, meaning f12 if I write, it will be 1, 2. The third index has to be summed over. So if I put 1, 2, k is getting summed over. It can take value 0, 3, 1 and whatnot. So if but any repeated index for antisymmetric tensor is 0, meaning epsilon 1, 2, 1 is 0, epsilon 1, 2, 2 is 0. Any repeated index would be 0. So when I do this kind of things, you will see that the k will take value only different from ij. So if I take 1, 2, k has to take value 3 only. So f12 will be the 3, which we have written like this. So this way we can write down from this antisymmetric derivatives all the terms over here which we have. So that is one thing which we can compactly write all the electric and magnetic field component using this field strength tensor F mu nu. One additional benefit of this is that apart from helping us in compactly writing electric and magnetic field components, this object F mu nu is gauge free, it is gauge invariant. That if I did the gauge fixing we had done, we are supposed to do in order to get the wave equation. But suppose we are not in that gauge where wave equation is manifest, even then the definitions of F mu nu does not change. So how to see that? Remember when we were discussing about the gauge freedom, we were discussing that vector A was supposed to undergo a change as vector A plus a gradient of a scalar, while the A0, which was the phi, the scalar potential, that is under that same transformation is supposed to change by the temporal derivative of the thing with 1 over c. So together we can see that it is asking us to change, like a mu goes to a mu plus del mu phi, del mu f or something like that. So you see A0 will change with 0th derivative, which is time derivative, and there will be negative sign between up index and down index. If you are careful about eta 00 is -1 and eta ii is 1. And the spatial derivatives will change with the spatial derivative, like from this term. It so happens if I write del mu a mu minus del mu a mu, that is the definition of F mu nu, you can realize that this object particularly does not change at all under gauge transformation. So if a mu changes like this, then the derivative of a mu will change like derivative of first term times derivative of the second term. And similarly here, the del nu of a mu will also change in a particular way. And again, an extra term will come from the derivative of f, but you will realize that both f dependent term coming from the first term and the second term are exactly the same, and partial derivatives commute. Using that fact, you can show that the F mu nu under the change of a gauge does not change at all. So therefore, it is manifestly gauge invariant object. I do not have to worry about which gauge I am writing electric field or which gauge I am writing the magnetic field once I have set down the definitions of F0i as magnetic electric field and Fij as magnetic field. And if I write down a Lagrangian, for example, in those things, or equations of motion in terms of F mu nu, those equations of motions will also be gauge invariant. Previously, I had written the wave equation which was true only in a particular gauge. But suppose I am able to write this thing in terms of function of some F mu nu, then I know whatever equation that is satisfying, it is a gauge invariant equation. So if I can express this whole equation in terms of the gauge, if I can express this equation a mu, box of a mu is equal to 0 in terms of F mu nu, then I know that that equation of motion is also gauge invariant. So therefore, I would not have to worry about which gauge these equations are written. All right. So this is a gauge invariant object. However, it is a rank 2 tensor. Lower F mu nu is rank 02 tensor, upper F mu nu is rank 20 tensor in terms of the Lorentz transformation. So A mu being a vector transforms as lambda inverse as like this. F mu nu Being a second rank tensor of the lower kind, it will transform with two lambda inverses, as we had discussed. And we had discussed as well how to make upper rank tensor from a lower rank tensor through contraction via the eta mu news. So that is how I will get the first index, second index here, using the first index here, second index here, and the remaining indices summing over. Now, the way we have seen it through, that it is a tensor quantity, it is antisymmetric, it is gauge invariant. The last bit is to write down the wave equation which we have. So remember, we have an equation of motion for electromagnetic fields. Dynamical equations of motions are these. The claim is that two equations which are dynamical equations of motions are just del mu f mu nu is equal to 0. You can verify. If you open it up, f mu nu, you open it up, use the fact that it is antisymmetric in the structure, you will be able to prove that these two equations are one and the same thing. So therefore, whatever Lagrangian I am going to write down, either I can demand that under variation of that Lagrangian I get this equation, or equivalently I can ask under the variation of that Lagrangian I should get this equation of motion. So those two will be the dynamical equations coming out from some Lagrangian's variation. And as we discussed, the remaining two set of Maxwell's equations are not dynamical equations. They are not supposed to come from some Lagrangian. Rather, they come from geometry. So therefore, you can write down something called a dual tensor to f mu nu by contraction with respect to the four index Levi-Civita tensor, epsilon, alpha, mu nu, alpha, beta. So this is also the same kind of Levi-Civita which we had previously seen. It is antisymmetric in pair replacement of any of two indices, and none of the indices can get repeated. So it will become cyclic. 1, 2, 3, 4 is 1, or rather 0, 1, 2, 3 is 1, but 0, 1, 3, 2 is -1, and so on. So using that, I can construct something called a dual, or Hodge dual, or a vector dual, or this is the dual to the f mu nu tensor. Now this dual f mu nu tensor equation, which is something like this, the divergence with respect to the second index of Hodge duals f0i will be 0, and this is just from the symmetry. If this is antisymmetric, this is antisymmetric, this is also antisymmetric, and that antisymmetric's derivative put together overall gives you something geometrical vanishing object, which is equivalent to divergence of b is equal to 0. When deriving divergence of b is equal to 0 in terms of either Hodge dual f mu nu or f mu nu directly with a multiplication of this geometric tensor, you will get the divergence of b is 0 automatically, irrespective of any Lagrangian. For all Lagrangians, this will come true. Similarly, for curl of E is equal to minus del B upon del T, again I write down the equation which is over here, and you can see that this is also equivalent to the another piece coming from the divergence of this Hodge dual f mu nu is equal to 0. You can verify. This is just a convenient way of writing. Don't get much dragged up into this tensor notations, because this is not the topic of the discussion for today. But I'm just writing in tensor notation for people to become familiar. Otherwise, we have just seen previously that this is just a manifestly 0 without anything physical we have to do. This will remain always 0 as long as B is a curl class vector and the definition of E what we had adopted remains the same. We do not care how they evolve in time, what Lagrangian drives them, nothing. These two set of equations will be true automatically. So therefore, the dynamical equations which we are going to go after is this equation, del mu f mu nu. These are four equations because mu has been summed over and nu is a free index. Free index can take various values, four values actually, 0, 1, 2, 3. The 0 value is divergence of E, Coulomb's law, and the nu is equal to the spatial index would be the curl of B equation, which is Lenz's law, let us say. Okay, so the flux law, if you want to call it. All right. So with this information, I'm just going to propose a Lagrangian, just like I have done the same thing for scalar field or the Dirac field. I prescribe you a Lagrangian which achieves for you whatever is required. Again, I do not claim as of now that it is the only Lagrangian which will be able to do that, but simple most, just like for scalar field or the Dirac field, we wrote down some simple most Lagrangian would be able to do that. So this proposal where I take f mu nu and self contract it, that means I take f mu nu, take its upper index version and contract them together. This is like writing f mu nu and this is writing f alpha beta, and using double copies of etas in Minkowski metric, I make them raised indices so that f mu nu come about. And minus 1 by 4 is put to make things consistent with the equations of motion which emerges out at the end. If you do that, you can verify that under the variation of its action, first let us do the variation with respect to A alpha. This A alpha will go in the whole action and search for wherever A alpha is appearing. And A alpha is not appearing anywhere, as you can see, it is just appearing in the derivatives. So what you can do, you can convert one of the derivative terms times this thing into a total derivative of this times this, which is f mu nu, upper f mu nu, minus the derivative hitting the f mu nu, which is this term, and a nu. So together, this two term generate for you this whole term, this times that. And similarly, together, these two terms generate this times that. So I have just conveniently written this in order to convert things into total derivative minus derivative of the first function. Right now, it is f mu nu and the derivative is hitting a nu. I use the method of integration or differentiation by parts, let us say, where I shifted the derivative onto the f mu nu and a nu became the free function. And now I can do the derivative with respect to a nu, which will give me this kind of a structure. Ultimately, this 4 factor exactly cancels with the 4 factor which will appear on the derivative. So this is just a simple exercise you should be able to do, and you will see really that indeed the equation of motion which we were after, del mu f mu nu or alpha, whatever you call, alpha is a free index, is equal to 0. So variation of this action indeed gives rise to the equation of motion of the first two or the two Maxwell equations which are dynamical equations. So this is a good Lagrangian, and this is the Lagrangian we will work with. Now, if you have done a course of electrodynamics and are familiar with the Lagrangian approach or a covariant approach, you would realize immediately that all these terms which are appearing over here or here can nicely be written in terms of electric field and magnetic field as well, because f mu nu ultimately tells you electric field and magnetic field. So if you write it down, you will realize that what we are writing is nothing but E square minus B square. Again, those of you are familiar with covariant Lagrangian formulation or a covariant formulation of electrodynamics, this E square minus B square in the units of C is equal to 1. By the way, I have put down epsilon naught and C and mu naught, all things to 1 as convenient in the usual notations. So in these units, E square minus B square is a low range invariant quantity. That's why the Lagrangian we have written, or the action we have written, is low range invariant. Okay, so you do get the equation of motion correctly from this. And one more thing you will realize, in this, del 0 a0 never appears, because del 0 a0 will demand this index and that index to be the same. This will make these two indices also the same. None of the diagonals are supposed to appear in any of the antisymmetric tensor. Therefore, this is a diagonal entry, del 0 a0. It will never appear. f00 is 0, f11 is 0, f22 is 0. So therefore, when f00 is 0, that means this is the place where del 0 a0 would have appeared, but it is 0, therefore it does not appear. So two things, I have a well-defined Lagrangian and I have a appearance that a0, del 0 a0 never appears. That means this is not a dynamical theory for a0. a0's derivative never appears in the Lagrangian. Okay, with this information, let us try to find out the momenta corresponding to the variable ai. I take the Lagrangian, which is this roughly, or which is this over here with 1 by 4 factor. And you can do the derivative of Lagrangian with respect to ai. Do this again, just like we have done for equation of motion here. And you will find out that you get f0i with a negative sign, which is equivalent to electric field. So the conjugate momenta corresponding to the ai, spatial ai, are the electric fields. ai and electric field are conjugate pairs, so they will have a phase space structure. ij, because ai will talk to its own electric field component. It will not talk to y or z if I is x. So this is ensured by the Kronecker delta, and position delta function is done like that. This is at the Poisson bracket level. Again, I'm rushing through, but I'm just writing the Hamiltonian of the same thing in the same approach. Here also pi 0 will be 0, because in the Lagrangian there is no term corresponding to del of a0 dot. Del of a0 dot is never appearing, so pi 0 is 0. So if you write down pi mu a mu dot and then work it out, this is equivalent to pi I ai dot, and then working out, because pi 0 never appears in the Lagrangian. So this is the Hamiltonian of the system. Again, you have this structure converting ai dot, which is appearing in this relation, writing in terms of pi I and the spatial derivative of a0. You can convert this back, and you can see that the total Hamiltonian has become the e square plus b square plus a total derivative term, not total derivative, divergence term of a0. That is the Hamiltonian density. That means total Hamiltonian will be just integration over the spatial volume d3x of this Hamiltonian density. And in this, I will have a e square plus b square. If you remember, this is energy density of electromagnetic wave, which integrated over d3x should give you total energy. But I have an extra term, which is del I a0 initially, del I a0 and d3x. Again, use method of converting the derivatives into total derivative, and on a0 you can flip this, the derivative on a0 into derivative on the EIs are coming along with it. So use again the same method which we did. Flip the derivative using a total derivative term, and you will get the total Hamiltonian. Apart from total energy density, contains an extra term, which is very useful, as we will see later on, in identifying a proper gauge and other things. And in that case, what would be the total Hamiltonian? So this is the classical Hamiltonian as of now, and we will try to see whether there is a case for quantum mechanics when we bring to it, whether we have reason to worry about this Hamiltonian as Spinors would have done. They got us into problems so that I had to modify the commutation relation. So with this extra term, I have to be really careful, because this runs the risk of making the total Hamiltonian negative, because other two terms are positive. If this term were not there, then I'm through. Okay. So therefore, I have to carefully analyze this term and what it does to the Hamiltonian, whether it converts it to negative quantity or not, and what in quantum domain, that we have to be aware about. That we will do in the next class. So let us stop over here with this information that I have a valid Lagrangian and a Hamiltonian out of it, and let us see what it gets us when we go to the quantum domain. Okay, so let us stop here.